So we want to define certain families of graphs that come up often. So the first family we're going to talk about are the complete graphs, and they're labeled with k sub n, and where n is the number of vertices, and the property that complete graphs have are that it's all possible edges on these n vertices. So let's draw a few of these. So k2 is telling me I need 2 vertices, and all possible edges between the 2 vertices, well, there's only one. K3 would have 3 vertices, and then the possible edges between vertices, well, I can connect this one to these 2 and this one, and then that's it. All the vertices are connected in every possible way. So each vertex is connected to all the other vertices. Okay, so as we get, larger number of vertices, these become more complex pretty quickly. So K4, so I got to connect this to every other vertex, but also have to connect this to every other vertex, and then I have to connect this to every other vertex. So there's the complete graph K4. And then K5, 5 vertices. I'm just going to organize these as sort of like the regular polygon, so like a pentagon. So I'm going to connect this one to all possible edges, connect this one to all possible, vertices, connect this one to the rest, and then connect this one. So notice each vertex is connected to all the other ones. And then K6, we'll do one more. K6, connect each vertex to all the other ones. And we'll stop here because they just get more and more complicated. But, I'm sure you can get on the internet, and there's plenty of pictures of all these. That messed that vertex up, but that's what it looks like essentially. So let's talk about another family, the complete bipartite graphs. So these are graphs who are bipartite but have the most possible edges while being bipartite. And remember, the parts of the bipartite graph we labeled as A and B, so these are the sets. Within these sets, we can't have any connections, but they can connect in between. And so that's exactly what this label is telling us. KMN, these are both integers. The first one's telling me how many vertices to put in my set A or column A, and the second one's telling me how to put in column B. And then remember, to be bipartite, I can't, so I'm going to put 2 in A for K23 and 3 in B. I remember the rule is I can't connect between them, I can only connect across, so I'm going to connect each vertex in A to all the vertices in B and do the same thing with the second one. And that's it. There's K23, right? I can't connect between them. That would be violating the bipartite rule. So let's see how this works for K33. So the only difference here is that I'm going to have one more vertex in set A, and I still connect everything in A to B, but not ever between things in A. And this is a famous graph that will actually come up a little later. And let's do one sort of weird one. Let's do K15. So there's 1 in this one, and then 5 over here. So I can't connect in between these. I can only connect this to each one over here. So we get a graph that looks something like that. And the last family we're going to talk about are cycle graphs. And these, the representations can end up looking like the regular polygons. So they're just cycles. So you can also think about them as circles with n number of vertices. So Cn is n is telling you how many vertices. So C3, I have 3 vertices, and I'm just sort of going a cycle around till I get back to the beginning. And notice that C3 and K3 are the same graph. For C4, it's not the same as K4. I still have 4 vertices, but I'm going around. I don't have the edges through the middle. And K5, similarly, I have the pentagon, but not the star shape in the middle. Right. And these are called the cycle graphs.